Welcome to a video on the Astable multivibrator or the square wave generator. So we will be looking at the working principle, then some derivations, do a problem and some simulations. So the Astable is a bistable which has been converted to be an oscillator. So a bistable has only two stable states. So we use the bistable circuit with a positive feedback. And then if we want to change it in astable, which is oscillating circuit, we need to flip this curve around so that we have a ball in here rolling side to side without ending, so assuming that there is no friction here. So basically, we add our energy as a bit of an automated system to do that. Okay, so how this works is this amplifier will have a saturated output either to the positive limit or the negative limit. So let's say this is to the positive limit. This capacitor over here will charge towards that limit. Okay, and in the process of charging, here is the input of our bistable. We will trigger our bistable and the output will switch to the negative limit. Then the capacitor has a new place to charge towards until it triggers the bistable again. So in terms of having this as a signal, if our output is, let's say, at L plus, our capacitor will start to charge towards our L plus. Okay, but it will reach this threshold and the output will switch to a negative and the capacitor has a new place to charge towards. So this charging and discharging of a capacitor is towards the limits, and that is determined by our RC time constant. If our limits are symmetrical, T1 and T2 would be the same. Okay, so we have a time for the charging and a time for the discharging, and the sum of the two would be our period. Okay, and that gives us our frequency. So in terms of equations, we can look at the charging of a capacitor. So V infinity is where our capacitor is charging towards, and V0 plus is where our charging is happening from, and then Vt is the voltage at a certain time. Okay, R1 and R2 determines our trigger levels. Typically, you will choose R1 and R2 to be the same value, having your beta at 0.5. Okay, so that is the typical choice. So this gives us our trigger levels, which will feature heavily in our capacitor charging and discharging, and our frequency is 1 over T. So we need to look at this thing from when the capacitor is charging and when the capacitor is discharging. So the voltage at T1 is when we reached our high trigger point. Okay, so we are looking at this point right here, and in the second derivation we are looking at our point right here. Okay, so the departure point would be from the lower trigger charging towards L plus for the first one, and our departure point will be the higher trigger charging towards L minus for the second one. Okay, so VTH is at T1, so we are charging towards L plus, and our departure point was our lower trigger point, and the time changed into this equation is T1. So solving for all of this, VTH is BL plus and VT low is BL minus, and we can solve to have T1 alone, giving us this nice Lin equation. Can do the same for the negative charging that is happening at T2. Our trigger point VTL, departure point VTH, charging towards L minus, solving for T2. Okay, so our final period is T1 plus T2. So adding these in the Lin equation, they will be multiplications. And typically, our L plus and L minus will be equal to one another in absolute terms, which will make that our equation is 2 times RC ln of 1 plus beta over 1 minus beta. So if beta is a half, this would be the ln of 3. Okay, and the ln of 3 is 1.1. So a typical equation that we will see for astables is 2.2 times RC is your period of this signal, is the period of a signal. Okay. So, what I want you to do is pause the video and analyze this astable here. If you can properly analyze something, you can most definitely design it. So, rail voltages of plus minus 15 volts. We have a saturation of 1.5 volts for this op amp. The zener that I placed in here is 4.7 volts at 16 milliamps, and the diode voltage is 0.7. So first I want you to find the output limits of this astable, and I want you to find the frequency of this astable. Then I want you to design a value for resistor 3. So that is the current that's coming out of this into our limiting circuit, into our load, into our capacitor circuit, and into our feedback. Okay, a hint here is that here we have a steady state over the resistor and the changing in the capacitor. So we want a maximum change in our capacitor to calculate the current. So pause the video and see if you can figure this out before looking at the solution. Right, let's have a look at the solution. The two resistors was the same, so the beta value is a half, making the period 2.2 RC, and our frequency will be 9.68 kilohertz. A 4.7 volt zener plus 2 times the diode voltage will be 6.1 volts, and the negative limit will be minus 6.1 volts. So there is our frequency and our limits. We will verify this in our simulation. Now, for resistor 3, we have VCC minus our saturation minus one of our limits over all the currents in the circuit. So the feedback, the zener, the load, and these two together, the steady state and the capacitor charging. So the zener requires 16 milliampere. In our feedback loop, we have the voltage drop across resistor 2, which is our limit, minus our trigger over R2, and that will yield 3.05 milliamps. The load is the limit divided by the load requires 6.1 milliamp. Then our capacitor and resistor. For the steady state, our resistor will want the limit minus the trigger voltage. Okay, limit trigger voltage. And that is the amount of current going to be drawn by the resistor in there. Then for the capacitor, we can use the change in voltage across the capacitor multiplied by 2 times capacitance and the frequency. So this will yield 1.38 milliamps. This would be from when you did rectifiers. This equation will look kind of familiar for the current in a capacitor. So we can plug all of this into our resistor equation and it will yield 274 ohms. So you can pick a 270 ohm resistor. I would rather go with 220 to ensure that we can supply enough current to all the circuitry required. So let's jump over to our simulation. So here I built the simulation of a circuit. 4.7 volt Zener, 220 ohm resistor for current limiting, 1 kilo ohm load, everything exactly as in the analysis problem. So if we run this, and we look here, we have 6.1 for our limits. And if we do a FFT on the output, our fundamental should be around, there we go, at 9.68 kilohertz. And due to the fact that this is a square wave, look at all these harmonics. Anywho's, so there's our frequency and our limits. Let's have a look at the current drawn. See, our Zener requires 16 milliamps. This requires 3.5 of 3.05 for positive and negative. And for the capacitor and the resistor, there is a bit of steady state, which comes from the drop over here and the change in the capacitor while it's charging. And there is the total amount of current in our resistor 3, which we did calculate close to 25 milliamps. And now I can go and change this to 270. You'll see that this is not changing at all. But the moment that we go larger, let's go to 470k, 470 ohms, sorry. There is a definite decrease in the current here, right? And if we have a look at our output, it started to decrease because we can't supply enough to the rest of our circuits, right? So if we keep increasing this resistor, we'll find that the output starts to drop because this Zener is not functioning properly. Okay, so this resistor is to properly protect our Zeners and to ensure that enough current is being supplied to all the circuitry so that we can function properly. And that is the Astable circuit. Thank you for watching.